So here is the outline of my talk. So first I will talk about this n equal to 4 superangles, maximally supersymmetric angles theory. Then I will talk about this operator deformation, and so we can have mass deformation of n equal to 4 superangles to reduce the number of supersymmetries. So we can get n equal to 2 star superangles. So there are other mass deformations as well. Then I will talk about lattice formulation. So how can we put this on the lattice in a consistent way? Then I will talk about the gravitational dual. So this theory takes part in ADA-CFT correspondence. Then I will talk about some results from literature. So there are people who worked on this gravity dual. So they have constructed the supergravity solutions and things like that. So they study with thermodynamics on the other side. So the question is, can we reproduce these things using this lattice formulation? So that would be a very nice test of this ADA-CFT correspondence. Then after that I will conclude and talk about some future predictions. Okay, so let's come to maximally supersymmetric angles. So n equal to 4 superangles in 4 dimensions.
Without gravity on one side, and on the other side we have this black hole, quantum black hole geometries. So there is a correspondence connecting the two, so that is the ADA-CFT correspondence. So dual gravitational theory, so in this 4-dimensional case it is a D3 brane geometry on this AdS5 cross S5 spacetime. So there are several regimes of this correspondence. So the regime we are interested in is when the gauge theory is strongly coupled. So when gauge theory is strongly coupled, on the other side, the gravitational theory is weakly coupled. So there we can have the supergravity calculations on the gravity side, but unfortunately we cannot have EC calculations on the gauge theory side because gauge theory is strongly coupled. So that is where we need lattice formulation or some other non-perturbative formulation of the theory. So coming to this validations of ADA-CFT correspondence. So in lower dimensions, so the theories were well explored on the lattice. So this matrix quantum mechanics BFSS model, which is in 1 dimension, 0 plus 1, then 1 plus 1 dimension. So people have explored this, including myself, to validate gauge gravity duality. So the simplest case is this D0 brane system, which is the supersymmetric quantum mechanics on the gauge theory side. So we have maximal number of supersymmetries. So it is 16 supercharges. So this is a BFSS model. So this is the plot from Masanori, Hanada, and others. So this is MC-MS collaboration, Monte Carlo M-theory, string theory collaboration. So they produce some nice results. So this plot shows, so this the data points, these are coming from lattice simulations. So here they are computing the free energy on the lattice. So from the gravity side we have this relationship. So in general we can write down the free energy like this, a series expansion. So there are some temperature power, temperature comes with certain powers. So these powers can be obtained through some scaling. Then the question is about the coefficients. So how can we get the coefficients? So we have obtained, they have obtained certain coefficients. So from supergravity we can get this coefficient A0, which is 7.41 something. Yeah, 7.41. Then there can, so these higher corrections, these can be quantum gravity corrections. They go like 1 over n square, and there can be string oscillator corrections as well. So to the leading order, so this is the quantum gravity correction we see here. So this is a prediction from supergravity without adding any corrections, any string corrections or quantum gravity corrections. So if you add more corrections, so there will be slightly moved away to the right. So these data points are coming from the lattice. Now we can fit to the lattice data points. So lattice doesn't know anything about gravity, but here, it knows, in quotes, about gravity.
T in units of G squared angle?
So it's a dimensionless T. So 't Hooft coupling, we take 't Hooft coupling. So in one dimension, it's lambda power 1/3, I think. Yeah, it's a dimensionless T. Yeah. Also energy. Everything is dimensionless.
So T small compared to 1 is where you expect gravity to be.
T, yes. There is a regime where supergravity is valid.
Which is your non-dimensional T much less than 1, right?
Yes, that is correct. Yeah. So T should be much less than 1. Yeah, so there are some limits. There's an upper limit and lower limit, where T should lie.
And T much greater than 1 is where perturbative angle is this right?
T much greater than 1. So we need to connect this to the coupling, okay? So low temperature corresponds to strong coupling. So yeah, so T much greater than 1, weak coupling, yeah, we can apply, yes, yeah, that is correct.
Is there any matching there near 1?
When you say matching, what kind of matching?
There is continuity, like sometimes these lattices are much below the non-perturbative or above.
Oh, right, perturbative matching.
Yeah.
Nobody has done this so far, so I don't know. Maybe you can, okay, I don't know. In the literature, nobody has done this type of matching for this theory. Yeah.
So is it whole form,
Hmm?
past term, the x0 term and x2 term, both of these come from ICTS-TIFR corresponding?
So this A note, it is coming from supergravity. They computed this. B note also, it has been computed from supergravity, some 4 graviton amplitude calculation. And so the higher ones, they are very difficult to compute, okay? So these powers are the temperature powers. So these are coming through some scaling arguments. So through that, one can easily find the powers.
You have a supergravity Lagrangian, which gives you the first term. Then you know that the next term is coming from some alpha prime string direction. Okay? So you know the structure of the term in the gravity Lagrangian recipe. So it's easy to get the power. To get the coefficient, you have to know the details.
Mm-hmm. Yeah.
Can one say that n squared term, 1 over n squared terms are not that much important? Is there ever
At lower n, when n is smaller, okay, number of colors, they become important. So they are like the quantum gravity corrections happening to this black hole. Okay, so at lower n, so to really see the quantum gravity corrections, we need to simulate the theory at lower temperatures and lower number of colors. So that's a difficult regime. So this theory has flat directions and things like that. So that can affect the Monte Carlo simulation. Yeah. Yes. Okay.
What do you mean by lattice? Is this the latest quantum mechanics?
Yeah, this is the BFSS model.
Yeah.
Yeah.
What do you mean by lattice? You mean
So we discretized the theory. So lattice is basically a circle. Okay. Yeah, it's a Euclidean lattice. So basically, what we have is a circle with lattice points on the circle, and we identify, periodic or antiperiodic boundary conditions.
and doesn't this theory have the sign problem?
So this is the maximally supersymmetric angles. On the lattice, we don't see sign problem. It is not that severe, but
Theoretically, it has a sign problem, right?
we don't know. We don't know. There is no analytical proof for this maximally supersymmetric angles that about the sign, okay, of the determinant, the Pfaffian. But for supercharge theory, the theory 2,2 in 2 dimensions, there people have analytically shown that it has no sign problem.
Wait, just a question of whether the determinant is real or not, you cannot establish that?
No, it's
Positive or not?
yeah.
You can't establish?
So here what you get is a Pfaffian, okay, square root of the determinant, and you can take the absolute value and phase, okay,
Yeah.
and we are interested in the phase.
Yeah.
The phase is telling us about the sign problem,
Yeah.
but so far nobody has shown this analytically.
Shown that it is zero.
Yeah, the phase is, the angle is 0, yes. So it is,
Do you suspect that that is true?
on the lattice we don't see any sign problem. So I suspect that this theory has no sign problem. Okay, but one has to show this analytically. So the problem is they look at the eigenvalues, and for this 2,2 theory, these eigenvalues, they come in complex conjugate pairs. But in this theory, it appears it doesn't come in pairs. Okay, it doesn't come in. It has some other structure. Maybe 4 of them. I don't know. So it is not that easy to, yeah. So we don't know, but numerical simulations, we check the phase of the Pfaffian, and it's nearly 0. So there is no severe sign problem, okay? Yeah.
So is the implication that as you go to fewer supersymmetries, you start seeing the more severe sign problems?
It depends on the theory. It depends on the structure of the fermionic part of the action, okay? So you integrate out the fermions and you look at the Dirac operator. So the structure is hidden in there. So it depends on the supersymmetric theory, which theory you are looking at. So some theory may have sign problems, some theory may not have sign problems. Yeah. Okay. So the conclusion is, Lattice is a very good tool to validate this ADS-CFT correspondence in this system. So we fit the data to what we have for the supergravity. So here we.
So we think that you really have under control of power.
Yes.
And the fact that there should be a 7.41.
Exactly. We need to reproduce that from the lattice data.
That would be in very small regions of P where you don't have.
Well, we have at least a few data points, right?
Starting from 0.4.
Right.
I don't know when we say P less than 1,
Mm-hmm.
much less than 1.
Right.
What exactly do we mean? I mean, like 0.4 is anywhere more than 0.
That is correct. It's a fit, okay? It's a fit to the data. So this is what simulations are giving us.
No, I
And we are,
understand.
yeah.
I understand. So
Yeah.
what I'm what further along
Yeah.
is that one can really work too. And I would
Right.
say that at this stage, the right conclusion would be that more simulations are needed.
Of course, yeah, I agree with that. So going to even lower.
The error bar, for instance, that should be taken seriously. 7.4 plus minus
0.5, yeah, it's a bit higher, yes, yeah. But
that's a serious error bar? I mean, one should believe that. If 7 became 14, you say that's not less than 14.
if 7 becomes 14, then yes, it's impossible. Yeah. Mm. But yeah, the mean value, it is.
Series with increasing speed.
Huh.
You can get it.
So you don't believe the error bar?
Look at the sign of A1 is negative and the sign of H is positive. And so if you have an alternating series which keeps increasing, eventually the measure comes in.
So,
Yeah. Yeah, same collaboration, yes, yeah. Yeah. Yes, they are improving the simulations, okay? So one has to go to larger lattices so that one can reduce this lattice artifacts.
What was the size here?
So here, how large the lattice is. Let me think. It is very high. It's really high. It's like 48 or something. Okay. Yeah. It's a huge lattice. Yeah. And number of colors minimum is 16. They started from 16. N equals 16.
What about the power? What about the fits to the power?
One could do that, but they haven't done it. They just fit to the coefficients. Okay.
The power itself, from the point of view of Gangman's theory, is a completely non-trivial.
Right. I would think so. Yes.
From the
So
quantum mechanics, there's no reason to expect this power.
yeah. Exactly. Yeah. This is
So-
coming from gravity. Yeah.
So,
Yes.
so when the zeroth order question is how well is the power being distributed?
Right. Yeah. So one could keep everything free, okay, and fit to this coefficient and powers. It'll be huge. Yeah. Yes. Yeah. It is huge. Yes. So anyway, at least people are trying. Okay. So we should encourage the community. Yeah.
Why are people not want to go to what is
The problem is problem with the flat directions. Okay. So the theory has this. So the theory has 9 scalars. So these are n by n matrices, and the Lagrangian contains this scalar commutator square term. Okay. And when these scalars, they can get this take this trivial configurations where this commutator is 0. So that means they can take arbitrary large values, still keeping it's 0. So these are called flat directions. So one has to control such directions. So that is here people are doing they add mass terms so that you have this confining potential. So once you go to lower temperatures, the problem is very, very severe. Okay, it will find the flight direction immediately, and then the simulation diverges. Okay, so to take care of that, one has to go even larger number of colors. So in that way, yeah, it's a simulation. One has to carefully think.
So going down in G is an unstable.
Yeah, it's problematic. Yeah, yeah, yes. So that's a problem with the flight directions.
But we actually are not generating that, like, how are you generating these different samples? I mean, it's not like hybrid Monte Carlo or something.
They are doing a hybrid Monte Carlo. Yes, yeah, yes. They integrate out the fermions. Yeah.
At 16 color, what is color? How many colors?
They start with the 16 colors and they go higher. Okay, various colors. Yeah, so here basically your fermion, it's like a 16 column Majorana matrix. Then you integrate out the fermions, you get the Dirac operator. Yeah. Then you introduce pseudo fermions. It's a standard hybrid Monte Carlo. It's quantum mechanics. Yeah. Yeah. Okay. So anyway, so this figure was so beautiful. So we put this figure in the upcoming program we are having at ICTS. So the figure is here. So there are some other figures. So there is a piece of code, so indicating that we need computers to simulate this, and this is some other non-perturbative effect. I think an instanton is breaking into 2 instantons or something. Yeah. So yeah, so there is a program happening at ICTS end of January. Okay, so a bit more involved case is this D1 brain system. So we go to 1 dimension higher. So this is the work I did with Toby Weissman and Simon Cattrall. People are still looking at this system. So here also we are able to show some good agreement with supergravity. So here there is this coefficient. This is unknown in supergravity. So the question is, can lattice simulations help? Can we provide some input to this?
What is RH? What is alpha?
So this is a 2-dimensional system. So it's like a torus. It's on a torus. So r tau is the temporal cycle, circle size, and Rx is the spatial. So Shiraz, you have also worked on these models back in the days.
I worked on it extensively, but I never used the notation Rx and alpha.
Okay. Probably use some other notation.
I still don't understand. What Rx and alpha is the radii?
Yeah, the dimensionless, yeah, in terms of in Thupft units.
Yeah.
So as we change the radii, so we have freedom. So these are basically like couplings. So we can change them, and we look for some phase transition in the gauge theory.
Oh, that Rx cube is that's the point of the phase transition. What is that?
So yeah, this is the boundary between confining, deconfining phases. Yeah, yeah, yes. So at high temperature, so the prediction is on a torus. Yeah. So maximally supersymmetric angles, we dimensionally reduce this to 2 dimensions, and we put it on a torus. Okay. So there is a temporal direction and a spatial direction. So at high temperature, we have this prediction. So Rx cube, it goes like this coefficient R tau. So Shiraz has also worked on these theories. So we have this prediction here. Then, so this prediction is coming from lattice simulations. So here, Rx square should go like a coefficient times R tau, and this coefficient is not known. Yes, yeah, in the theories, and it has a meaning on the gravitational side, which is like a black hole, black string type of transition. It's a topology changing transition happening there. So people can do supergravity calculations and come up with this coefficient. I think it's not that easy. So this is also another case. Yeah, Shiraz.
It's not. It's a bit misleading to call it confinement deconfinement. It depends on confinement deconfinement in the way. So let me explain. Suppose you've got it on a torus. You've got time and space. Now you go at least the limit I understand is this. We're going to a very high temperature. But the time surface is very small. So you can integrate to that. So it becomes effectively like quantum mechanics in the spatial age. Euclidean quantum mechanics in the spatial age. Then Euclidean quantum mechanics is like bosonic matrix quantum mechanics, which has a confinement deconfinement term. Okay. Now the parameter, the effective coupling of that bosonic quantum mechanics is related to the size of the X surface because of dimension. That's it.
Okay. So now we can go to higher dimensions. Okay. Yeah.
At decoupling, this is a sort of double wave function. You have a second order wave function followed by a third order wave function.
At recoupling. So there is a Gross-Witten-Bardier transition in the system.
There are two.
Two of them.
Very, very closely spaced.
Okay. Yeah, we haven't looked at that.
That kind of thing was not.
No, we haven't looked at that. So yeah, that is something to look at in the system. Yeah. Yes.
But there was some numerics.
Agreed with that. Yeah, so that's
Oh, but that's just in the quantum
guys
mechanics.
of Nishimura, they do find this double transition.
Okay.
That their order was split initially,
Okay.
but after they did
After Gautam correct.
more carefully,
I see.
so it turns out to be two transitions, second order followed by a third.
I see.
That's the simulation just of the quantum mechanics. Just of the 0 plus 1 dimension.
No, SFOs.
But they actually,
They're
they probably simulated just the 0 plus 1 dimension. So this reduced it. Yes. That's the bosonic simulation is very easy compared.
Yeah.
There were no fermions left. I think that this will be much harder to get this actually.
It's just the bosonic wave.
Yeah.
Okay. Yes. Okay. So that may be hidden in here. Okay, in the system. Yeah. Okay. All right. So then we can go to higher dimensions. So this is just to give a motivation. Okay, what is there in higher dimensions? So we can go to D2 branes, systems with the D2 branes, other exotic realizations. So this paper, this figure is taken from this paper with Morita, Shiba, Weissman, and Withers. So here they talk about various phase transitions happening in the gauge theory, okay, in terms of the coupling and two coupling, spatial and temporal. So there are exotic realizations, so one can do, there is room for more simulations and explorations. Okay, now coming to the main part of the talk. So Maxwell supersymmetric angles in 4 dimensions. So the field content is.
Just before you start this.
Yeah.
So suppose you wanted one place to get, precision numerical tests for supergrammar. One thing. Which would be the easiest place?
I would say 0 plus 1 dimensional theory. Okay, it is much easier to simulate, and it captures almost all of this interesting physics. Okay, so one can learn a lot from this system. Yes. So coming to 4 dimensions. So n equal to 4 super angles in 4D. So it contains a vector multiplet, and it has 3 chiral multiplets in terms of this n equal to 1 language. So vector multiplet contains this gauge field and wild fermions, 2 of them. Then the chiral multiplet, S is running from 1 to 3. There are 3 of them. So there are scalars and again fermions. So this theory has a global symmetry group, which is given by this SU to left cross SU to right cross SU4. So this SU to left cross SU to R, it is a Euclidean Lorentz symmetry. So locally it is SO4 rotation. Then SU4, it is an internal symmetry group. So where we can rotate the fermions and scalars internally without depending on space-time. So this is locally SO6. So this is a global symmetry group of the theory. Now we can, so this n equal to 4 super angles, it has 16 supersymmetries. So we can break these supersymmetries by adding some operators, some mass deformation. So we can break this into 16 to 8 or 16 to 4, various ways we can do this. So it was described in this paper by Polchinski and Strassler. So here we are focusing on this n equal to 2 star super angles. So you might ask why it is called 2 star, why is there a star? So this theory is, it's a non-conformal theory, and it is between n equal to 4 and n equal to 2. So this theory actually flows. So in the UV it becomes n equal to 4 super angles, and in the IR it becomes n equal to 2. So since it's something in between, so people call it they call it n equal to 2 star. Okay. So we can combine, so how do we construct this theory? So we can combine the two chiral multiplets to get an n equal to 2 hypermultiplet. So the action of the theory is n equal to 4 plus some mass terms. And this mass deformation, it takes this particular form. So there are fermionic mass terms, scalar mass terms, and Yukawa couplings. So the question is, can we put this theory on the lattice in a consistent way? And we can simulate the lattice theory at finite temperature and get some interesting information. Yeah, here we have same M, but there are various options. One can consider maybe M1, M2, M3, or M1, M2. Sorry, in this case, M1, M2. There are two.
Choice, not the specific way the M2 star is coming.
So when we say n equal to 2 star, it has to be same M here. If you have, say, M1 and M2, it will not be supersymmetric. It will not preserve 8 supercharges. Okay, it will further reduce the number of supersymmetries. Yeah. So here all M's are same in this case. Okay, so it is convenient to express this mass deformation.
Okay, sorry,
yeah.
This is a very ignorant question. I'm sure nobody will be able to.
Yeah.
But with n equals 2 supersymmetry, you can't add a superpotential.
N equal to 2 in 4D.
Yes.
Mhm.
So how do you get the mass term? What is the origin in superspace of the mass?
So basically, yeah, in superspace language, so you have 3 chiral multiplets, phi 1, phi 2, phi 3. So you have this superpotential of that, commutators of that.
Yeah.
On top of that, you add, say, M1 phi 1 square plus M2 phi 2 square. Okay.
Yeah, naively that breaks it down to n equals 1.
If these are M1 and M2, yes, if they are different.
M1, what I'm not understanding is why, superpotential,
Yeah.
normally you cannot add independent of the Taylor.
Okay. Yeah.
In n equals 2. How do you? It's a very
So-
stupid question. Does somebody know?
So the way I know is you add this M square phi square. Okay. M square phi 1 square plus M.
One language.
Yeah. N equals 1 language. Yes.
N equals 2, I think it has to, this is gauging the Euclidean issue. It's giving the rest to the
Okay, thank you.
I see. I
Thank
see.
not of the scalar.
I see. Okay.
Thank you.
Okay, so instead from the other side, the gravitational side, so we can split these mass terms into 2 operators. So we call this O2 and O3. So basically this is splitting of these mass terms. But this phi 3 comes here. Here also we have phi 3, okay? So phi 3 does not take part in this n equal to 2 star deformation. It is part of the vector multiplet. But somehow one can, so these 2 operators, they have meaning on the other side. So they correspond to turning on bosonic and fermionic scalars dual the gravitational theory.
How
So
much of the R symmetry, if any, is preserved?
so there is, I will talk about that. There is an SU2 cross U1 symmetry. Yeah. So the action of the n equal to 2 star, we can write this in this way: n equal to 4 action plus these operator deformation terms. So there is soft supersymmetry breaking induced by mass terms. So when m goes to 0, we recover n equal to 4 superangles, which is in the UV. So there is a strong couple. There is a mass scale that is developed in this theory, this n equal to 2 star theory. It's similar to this lambda QCD. So in the UV, it becomes n equal to 4 superangles. It's a conformal theory, and in the IR, it becomes n equal to
O2 is
superangles.
raised by 2 square.
Trace phi 2 square. I think it's a linear combination of. Yeah, it appears as a linear combination of phi squares here.
Okay.
Yeah.
So if the 2 chiral multiplets
Yeah.
that are in the hypermultiplets are, let's say I call them phi 1 and phi 2.
Yeah.
O2 and O3 are linear combinations of quadratic terms in phi 1 and phi 2. Cubic.
O3 contains this Yukawa type of terms. Okay.
The previous
Yeah.
example,
Yes. Yeah. Yeah. So it contains these extra terms. Okay.
Oh, I see.
Yeah.
I see.
Yes.
And here in this slide, that is the mass term.
So this entire thing is part of the mass term. Okay. The mass deformation.
But which part of this is in the O2 list you have?
I would.
After.
Yeah.
I see. Thank you.
Yeah.
that has n square over 3. This one will have a 2 n square.
Yeah. Yeah. They cancel. Yeah.
I see.
Okay. So coming to putting this theory on the lattice. So we can. Yeah.
What's the
I will come to that, okay? I will explain what it is. So we are interested in putting this theory on the lattice and simulating this at finite temperature and studying some thermal phases happening in the theory. So the way to put the theory on the lattice is you twist the theory, okay? The thing is, naive discretization of supersymmetric field theories, it breaks supersymmetry once we put this on the lattice, because we have this Q with Q bar equals P, and P is the generator of infinitesimal translations, and we have no notion of infinitesimal translations on the lattice. So naive supersymmetric theories, it breaks supersymmetry once we put such theories on the lattice. So we need to do something clever. So people thought about it. So they came up with this, using the idea of topological twisting, which was introduced by Witten in 1988. And so once we twisting is basically mixing this Lorentz symmetry group with the internal symmetry group, basically locking in these two symmetry groups. So whenever you make a Lorentz rotation, you make an internal rotation at the same time. So that is basically what twisting means. So n equal to 4 super-Yang-Mills can be twisted in 3 different ways. So one is called half twist, and the other is called Waffa-Witten twist. So this is a twist Waffa and Witten used in this S-duality famous paper. And the other is the geometric Lagrange twist. This is also known as Marcus twist. So these choices are given by how we embed this SO4 in SO6. So we have n equal to 4 super-Yang-Mills. It has this SO6 internal rotation symmetry, and it has SO4 Euclidean Lorentz symmetry. So we need to, so twisting is basically taking the diagonal subgroup of SO4 cross SO4, and we need to embed this SO4 in SO6. So there are various ways, and there are 3 ways to get a scalar supercharge, and these are these 3. So twisted and untwisted theories, they are equivalent when there is no curvature, okay, on flat R4. The question is what happens when there is curvature. So if you put this on a curved manifold, only scalar supersymmetry is preserved, okay? The others, they deviate away. So these theories, they are inequivalent, okay? They give rise to different theories. So the same thing happens on the lattice. So on the lattice also, only scalar supersymmetry is preserved when you put this theory on the lattice. So there is some deep connection between, you know, once the manifold is curved, once there is gravity, and we have a lattice formulation of space-time. So maybe it is telling us something about quantum gravity, you know. It is space-time is, I don't know, discrete or something.
The scalar supersymmetry squares to 0?
Yeah, squares to, it depends on the twist, okay? So in geometric Lagrange twist, it squares to 0. But in Waffa-Witten, it squares to 0 up to a gauge rotation, okay,
right,
which we will see.
So that's why it can be preserved.
Yeah, yes. Yeah. So we will use Waffa-Witten twist. So before the twist, this is a symmetry group, SU2 left, cross SU2 right, cross SU4. Then after the twist, we get an SU2 prime left, cross SU2R, cross SU2F. So here I break this SU4 into SU2I, cross SU2F. Sorry, I didn't put the indices. So basically, this is a subgroup of SU4. So then this SU2 prime, it is the diagonal subgroup of SU2 left cross SU2I. So basically, we are embedding an SO4 into this SO6 in this particular way. So this is the Waffa-Witten twist.
So you're putting this R4 in a unique box,
On the lattice? Yes, we have to think about, suppose we want to introduce temperature, okay? Then we need to pick one direction where we put antiperiodic boundary conditions for fermions. So basically, it's a torus. Lattice geometry is a torus.
So theory is okay with putting boundary conditions on
Yeah. It's so, yeah.
It's a tangent space. The boundary condition, at least in principle.
or it's just labeling
It's just a tangent space.
labeling.
Yeah.
Okay, so once we twist, what we have is the twisted fields. So here A mu, it doesn't change, the gauge field doesn't change. Then the fermions, the wild fermions, they become twisted fermions, which I give like this. So there is an eta, zeta, these are some scalar fermions, some Grassmann objects. Then chi mu, psi mu, so these are some self-dual fields. There are 3 independent components in each. Then there is a psi mu and a chi mu. So these are vector type fermions, okay? So basically, it is changing the spin of the field, but still they are fermions. They are Grassmann type objects. Then the scalars, 6 scalars, they decompose in this way. B mu nu, it's a self-level field. It has 3 components. Then phi, phi bar, and C. These are scalars. So total, there are 16 fermions in this theory. And twisting doesn't change the number of fermions in the theory.
Twisting doesn't also change the recurrence physics. I mean, some kind of a consistent function or simulation function of n gamma is supposed to change that twisting doesn't change anything.
So like you said, in flat R4, twisting is just a change of variables. It is the original theory. Okay. So twisted theory, it's an exotic realization of this global symmetry group on a flat R4. Okay.
Flat also you can actually show that that is.
Yeah. Yes. That's what we are doing also. Yeah.
There is a dictionary between twisted theory, observables of twisted theory and the untwisted theory. There is a dictionary between the observables,
I see.
between the twisted and untwisted. Usually on a curved manifold, most of the observables of the untwisted theory do not survive. Then in R4, there is more to untwist.
Yeah.
Eventually, it turns out to be the Euclidean variant observables, which are the good observables.
Right. I mean, on the lattice also, that's what we need. We need observables to be gauge invariant. Okay. Otherwise, they are not physical. So
just to say that a little more, there's a spin connection that tells you how component of the fermion changes you take from place to place. And what you do is you turn on a background gauge field for a global symmetry group to make that equal and opposite to the spin. That's what twisting is.
And it's a background global gauge field. The global is
The twisting. Yeah. Now, in R4, you keep the spin connection to 0. You turn on the background gauge field, that's to 0. It doesn't matter.
okay, so twist gives 2 scalar supercharges, which I denote by Q and Q tilde, and they squares to this particular form. So these are gauge rotations up to the scalar field phi. For Q square and for Q tilde square, we have similar gauge rotations with phi bar. So what we have is, so the question is, what do we call by R symmetry after twisting? Because we already took a part of the R symmetry for twist. Okay. So here SO6, it breaks into SO4 comma, SO4 and SO2. Okay. So there is a remaining SO2 symmetry. Okay. But here the notion of R symmetry changes once you twist. Exactly. You mixed R symmetry with the Lorentz symmetry. Yeah.
And you said this, but before twisting, the mass deformation leaves SU2 like SU2 times U. Is this right?
Mass deformation, SU2 cross U1.
Just SU2 cross U.
Yeah. Because it breaks, so there are 4 wild fermions and there are 2 massive wild fermions, okay, once you give mass. Yeah. So it breaks.
We turn on the mass deformation is by weakly gauging one group of SU4 substratum. So SU2 times U1.
Right.
So
Yes.
then you can only twist on manifolds such that the spin connection lies in one of the 2 SU2s.
This is a twist of input force.
Right. Yes. I will turn on the mass deformation later. Okay. So that will be added to this. Okay. Yeah. All right.
Say you're going to twist this theory.
Yeah.
Since you don't have a full SU4 R symmetry,
Yeah.
you can't compensate an arbitrary spin connection.
Okay.
So you can only then do the twisting of special manifolds. Is this right? In this case? Where the spin connection lies inside SU2 by U.
But he's doing R4.
I'm doing R4. Okay. So I don't have to worry about that.
No, but just to understand.
Yeah. Yes. Yeah. Yeah.
What it means.
Okay. Scalar manifold. So there are Q supersymmetry transformations, the twisted supersymmetry transformations. They take this particular form. So Q acting on A mu is psi mu. So here A is the connection, and psi mu is a one form fermion. Then Q on psi mu is d mu phi. Then Q square on A mu is d mu phi. So it closes up to phi. Okay. So similarly for other fields. So here H mu nu and H mu. So these are some auxiliary fields introduced. We can integrate them out once we write down the Lagrangian. So similar transformations for Q tilde. So we have 2 scalar supercharges in this theory. So that is a property of Waffa-Witten twist. In Marcus twist or geometric Lagrange twist, we have only 1 scalar supercharge. Okay, so this action of the theory takes this particular form, n equal to 4 action Q with Q tilde acting on a functional, which gives us the action. and this function is called an action potential, and it has this particular form. So once we apply Q tilde and Q successively, and we recover this twisted n equal 4 action. So mass deformation of the untwisted theory, it has this form, and once we introduce mass, we need to modify these Q transformations so that it is Q invariant. Okay, so let's modify the Q transformations. So I'm sorry, there are too many questions. So the modified Q transformations, they look like this. So basically, we are giving mass to one hypermultiplet of the theory. Okay, so that is reflected here. So the Q square algebra, it is also modified. Okay, it takes this particular form. There is a mass appearing here. Okay. So once we have that, we can write the action of this n equal to 2 star theory in this Q exact form. So when we say Q exact, we get the action when Q acting on something. Okay, Q acting on a functional of the fields, and that functional is this. So this is called a gauge fermion in the terminology. So once Q acts on the gauge fermion, we get the full action. So there are some there are some fields, some functionals appearing, so they take this particular form. Self-dual, yes. All the two form fields are.
So to comment that,
yeah.
then the thing multiplying it will also be definitely the self-dual part.
F mu nu is self-dual, yes. F nu,
So
yeah. Entire thing. Yeah.
You see that the action localizes on the self-dual.
Yes, of course. Yeah, it does. That's a property of this theory. Yeah. So it localizes on incident configurations. Yeah.
So the action can be built up.
Yeah.
By trying to write down an action which localizes on the self-dual.
Yeah, from the very beginning, yes. One can do that. People do that in topological field theory language. So they start from something simple, okay, this instant equation, and they gauge fix a series of gauge fixing, and we can reproduce this action. Yeah, yes, that is possible.
What does MQM stand for?
So M stands for mass, okay. So mass dependent, that is what it means. Yeah. Okay, so this is a full n equal to 4 action. On top of this, we can add the mass terms, okay, in the twisted form. So here, yeah, the mass deformation, it takes, so the twisted form, it takes this particular form, okay. So here we see some free indices. One thing is, it is not Lorentz invariant, twisted Lorentz invariant on the lattice, because these free indices are coming out, okay. So that is a property of this particular, once we try to put this n equal to 2 star on the lattice. So this, it is not twisted Lorentz invariant, but it has all other good properties, like there is no fermion doubling problem, it is supersymmetry invariant, it is gauge invariant, it is local. Okay.
Sorry,
So
I didn't understand. In the continuum, it is Lorentz invariant. It is
yes,
Lorentz.
yes.
So what about the lattice point?
On the lattice, once the mass terms, so some of them we can see these free indices coming out, okay, for some terms. Okay, so ideally we would, I mean, it would look more beautiful if the indices are summed over. Okay, so maybe there is a way to make it in a Lorentz invariant way. Okay, to express this.
Why is the free indices are the same it is Lorentz invariant?
So in the continuum it is. So in the continuum untwisted. Okay, sorry.
I'm talking about twisted.
Twisted one in the continuum also it is not Lorentz invariant.
Okay, so
Yeah,
it's not
yeah.
the lattice.
No. Yeah, it's a twist itself. Okay.
Why isn't it Lorentz invariant?
It is the way the fields appear. Okay, so basically, twisting is a change of variables.
Wait,
So
I thought twisting was identifying some linear combination of the original Lorentz group and some R-symmetry group
yeah,
with the new Lorentz.
yes,
Since the action was invariant under both the original symmetries,
yeah.
how can it not be invariant under the combination?
So here you can, yes. So one can find a way.
Yeah. Essentially a gauge transformation, but with also with asymmetry compensating factors. So the idea is we have explicitly broken one part of the Lorentz invariant to take it back.
Right. Yes.
So only that will be manifesting this form. But we try to do a Lorentz transformation with one broken part. It involves redefining the fields. Under that.
This redefinition is a gauge function? I mean, you're not saying isn't it just manifestly?
There may be a way to make it Lorentz express it in a Lorentz invariant way, okay? So I haven't figured it out yet. So
But if there is an explicit Lorentz invariant way of expressing it, then there is no way why we should be able to do it on the one.
that is correct. Yeah, we need to focus on,
Statement
yeah.
on A,
yeah,
whether the two-state theory is or is not Lorentz invariant. Whether you, whatever that Dirac says, Lorentz prime, whatever you want to call it.
right, yeah.
If you say it is invariant, then under the same Lorentz prime, that is
Yes, I agree with that. Yes, that is correct. Yes. So here, what is happening is, I will tell you why the sum of the terms are not, there are free indices, okay? So what we do is, so there is a, so we take the fields of the untwisted theory, and these are linear combinations, okay? To make a twisted field, it's basically taking linear combinations of the components of these untwisted fields. And then we can rewrite this untwisted mass term, okay, in terms of these new variables. And that is what we get here. So there are Lorentz invariant terms, so twisted Lorentz invariant terms, which are this, and there are terms that break Lorentz symmetry, okay, twisted Lorentz symmetry, and they are this. But they may be invariant under some discrete rotations on the lattice. If you put it on a hypercube, and if you perform some discrete rotation, it may be, we get the same action, okay, which I haven't looked at it yet. It may be possible, okay. Okay. So appropriate for lattice, so how do we put this theory on the lattice? So we can look at something called balanced topological field theory form. It was introduced by Digraph and Moore in this paper. So basically we introduce 3 vectors. So these are all self-Liouville fields, the 2 index fields. So there is a 3 vector phi, which is a functional of this F mu. Then there are 3 vectors corresponding to the other 2 index fields. Then in this language, the action potential, it takes this particular form, okay? So basically there are 3 independent components for, say, F mu nu or chi mu nu fields like this. So we can use this language. So now discussing this on the lattice. So there is this lattice prescription provided by Sugino back in the days, I think in 2003. He was looking at putting n equal to 4 superangles and n equal to 2 in 4D on the lattice. And he gave a prescription to put such theories on the lattice. So now this is known as Sugino's prescription for lattice. So gauge fields, they live on links. So in lattice QCD, it is familiar to us. So U mu, which is taking this, it's a map from A mu to a link field on the lattice. And the links, they live on sites, between, it's not a link, it lives on a link. Then all other fields, they live on sites. So the lattice theory we obtained this way. It is local, it is gauge invariant, and it's doubler free. It's free from Fermi doubling problems. One can also show that. Sugino has shown that, and we are using the same prescription for this theory as well. So it has all these nice properties. It is also supersymmetry invariant under this QM supercharge. One supercharge is present on the lattice. But it, as I showed, there are some terms with open indices. One of the SU2s. So on the lattice, what we need is a discrete rotation. So it may be possible to keep a part of the twisted Lorentz symmetry on the lattice, which I haven't looked at it yet. Okay, that is another thing to do. There are so many things to do from this construction. So one could make use of such discrete rotations, and we can control these additional operators that come on the lattice. Okay, when we look at the renormalization and things like that.
So we have a continuum action.
Yeah.
Which is not manifestly invariant in the Lorentz symmetry.
Continuum twisted action. Yeah. Yes. Yes.
So
Yeah.
because we took an asymmetry and identified it with context, it goes on to the Lorentz field.
Right. Yes. Yes.
Sorry, I still haven't understood that. Why don't we then, under the modified transformation, why isn't it manifestly?
Will M term.
It is the mass terms. Yeah. The mass. Yeah.
So for your question is valid if it is massless. At the mass level, when you are made explicit charge, then the transformation is spoiled.
It could be that. Yeah. So yeah, I need to explore this further, okay? It is the, so the way we introduce the derivatives, okay, so there is a d plus, I will come to that, okay. So one can actually show that there are no fermion doublers appearing in this construction, okay. There is a rigorous derivation. Suginov has done that.
But you haven't shown the particular term which does not allow this yet, right?
A particular term?
You haven't shown that there is a combination of derivatives yet, right?
No, I will come to the lattice transformations. Yeah. Okay, so again, these are the lattice transformations under this balanced topological field theory form. So here we can see these covariant derivatives, they are replaced with the d plus, d minus, okay, so these forward backward difference operators. Yeah, this is only one that is perturbed on the lattice. Yeah. Yeah, so out of 16, we have only one perturbed on the lattice. Now we can ask, is this good enough? Huh? N equal to star, yes, yeah. For n equal to 4, there are two. There are two scalar supercharges perturbed on the lattice. So once we give mass to half the hypermultiplets, that the other one is gone. Okay. So still we have one supersymmetry perturbed. So we can ask questions like, can we recover all supersymmetry, all 8 supersymmetries in this lattice theory as we approach the continuum limit? So these are all, these questions should be answered. So these are the next things to do. Yeah. Okay, so covariant derivatives, they become covariant difference operators. Their rules are given here. So straightforward to write the lattice action. So basically, this is a form of the lattice action. Okay, it is Q acting on a gauge fermion at a lattice site, which will give us this n equal to 2 star lattice action. So here beta is the lattice coupling. Okay, it is related to 1 over g square and some other terms on the lattice. So lattice action is local, doubler free, gauge invariant, and twisted Susy invariant. Okay, so these are all nice properties of a lattice construction that can have.
So, if you do this thing, then so you said that Q comma Q would be C, and
Yeah.
it would be the thing, and you are avoiding that. How? Go back to the
So
transformation. Yes.
yeah. So what we can do is we can apply Q on S. Okay, apply a QM on S, and that QM comes here, and it becomes Q square M. Okay, and Q square M is nilpotent up to this the gauge transformations given by phi. Okay.
Isn't it that normally it's Q with Q bar that's Q, and Q with Q is 0?
But this is not the same Q. This Q is different. This Q is a 0 form supercharge. Okay, it's not a spinor.
I understand. 0 form once you re-identified your Lorentz group. So suppose I trace it back to what it was originally.
Okay.
Wouldn't it be just one of the Q's that?
No, it will be a linear combination.
A linear combination of Q and Q bar?
I don't know which it is. It will be we can find that out. Okay.
You can write it down.
Yeah, please.
So in n equals 2, we have let's say QA alpha and QA.
Q bar alpha dot. Huh? Yeah.
So we use an epsilon. We use an epsilon tensor with these mixed indices, which is identifying this SU2 with the asymmetry SU2, and then contrasting with that. That is that scalar.
Yes.
It's a linear combination of Q and Q bar.
This should be a Q bar, right? Q bar.
This is only Q bar.
This looks, yeah, there's only Q.
So then obviously Q bar is basically. Well, you need a Q with a Q bar to get a non-zero momentum. So then only Q bar. This is a linear combination of 2 Q bars. So it's not surprising that there's a supersymmetry request to give. There always was.
So
So it's just to get an algebra out of the T.
But you have to be able to consistently preserve something which is only a Q. Not a Q.
okay.
In this case, only a Q bar.
But with this introduction of this mu epsilon symbol, the other Q's will get here.
Yes, they all mix. Okay, these are all linear combinations. Yeah. But other supersymmetries, they are not perturbed on the lattice because they break gauge invariance on the lattice. so that we cannot have them on the lattice. Yeah, so this is a lattice action. It is twisted supersymmetry invariant, okay, under one supercharge. So then there are some problems with this lattice construction. So if you look at the gauge action, it has this particular form for this theory. But if you look at the standard Wilson action, it has this form. So here, we look at the minima of this. So it can have many classical vacua. So these are all the minimum configurations for this. But for the Wilson, there is a unique minimum, which is given by this. So this twisted theory on the lattice, it has so many minima. So we need to pick one. Okay, so that is a problematic case. So we could resolve this by adding a standard Wilson term that will bring everything to this unit configuration. Okay. So that means we are adding an additional parameter. So it comes with a coefficient. So we have one more parameter to tune. Okay, so that is one way. Because this is a feature of this, yeah. You wouldn't have, yes, you will get the, it depends on how you discretize.
Yeah, that you did when you put the supersymmetry on, and now you break it.
Yeah.
So,
this is one way, okay. There may be other approaches which are supersymmetry preserving, okay. So there is an approach given by Sugino, Fumihiko Sugino and So Matsuura. It's called the admissibility condition, and it is a supersymmetry preserving way of picking this unique vacuum. Okay, so that is basically you pick certain gauge configurations that satisfy this certain condition. Okay, so there is a supersymmetric way to do this also. I am exploring that option as well. Okay, so this is the easiest option. So simply we look at, okay, we have a Wilson term, we can add that term. Okay, that will bring this to this unique minimum. So it will break supersymmetry on the bosonic sector. Okay. So the question is, you have to fine tune. You have to fine tune the coefficient once you approach the continuum. So when you see other properties, what, doubling problem? No, that will not change. Yeah. So what we can see is there is an additional parameter if you introduce this particular term. Okay, and we have to fine tune that. It is the center of SUN. Okay. Yeah. Okay. Now let's talk about this gravitational dual. I am not an expert on gravitational dual. So the dual was constructed by Pilch and Warner. So there is this Pilch-Warner geometry. So it's a product of deformed ADS5 and a deformed phi sphere. So it has this isometric group given by this HUD cross U1. This is also the R symmetry of the nuclear 2 star, like Shiraz asked. So we can identify this as a symmetry group. So this SU2 acts on two massless fermions, and U1, which mixes the two massive fermions. So there are two supergravity scalars. So this is coming from this n equal to 8 gauge supergravity in 5D, and we can add various scalars to deform this solution and to get various gauge theories on the boundary. And we can add two scalars. They correspond to these operators I mentioned, O2 and O3 in n equal to 2 star. One is a bosonic and the other is a fermionic in quotes. So supergravity action, it has this particular form. Here G5 is the Newton's constant. L is the radius of the phi sphere. R is the Ricci scalar. Then there is a matter Lagrangian, which is given by this. Again, these two scalars, alpha and chi, they appear. Then potential is given by this. G hat, the supergravity coupling, is given by this. So these are all the things happening on the other side. There's a superpotential which contains this alpha and chi. Then what can we do with this lattice construction? Can we give some input? So we can use lattice n equal to 2 star superangles to validate the duality. So Pilch-Warner solution at finite temperature can be put in finite temperature. To this, it was constructed by these people. And they also, these people solved the supergravity geometry numerically at finite temperature. So we can compute various quantities. They also computed it, them on the other side. So there is pressure, which goes like T power 4. So here this F is a scaling function. It has a profile, which they computed. So there is a dimensionless parameter, which is M over T, that appears in the numerical simulation.
I'm sorry, my vague memory from long ago was that the zero temperature solution has some strange properties in the IR. It's a puffed up braid.
Could be. I don't know.
So all this is cut off by the finite temperature. This is just
probably.
supergravity?
Yeah, this is finite temperature, yes.
Yeah. And is there a minimum temperature after which the solution is?
Probably there is. So Larry Yaffe, they talk about going to lower temperatures. And they say that it's a big achievement going to this. So I don't know what exactly happening
And
there.
the R symmetry, is it all preserved in the solution?
Finite temperature supersymmetry is broken, okay, by the temperature.
SU2 can be one. Preserved.
That I don't know. I would say it is also broken by finite temperature.
Well, typically at high temperature is preserved.
Okay. I don't know. I don't know the answer to that. So thermodynamic quantities, we can compute pressure, entropy, density. So they have this power law behavior with temperature T power 4, T cube, and there are some profile functions. So these figures are taken from this paper. So we can compute the equation of state, which should go like this with another profile function, omega, which is given by this. So here, the specific heat to entropy ratio, which is given by this. At low temperature, it should reach this value. This is required by conformal invariance. So the theory becomes n equal to 4 here when mass equal to 0. So they produce these nice results from supergravity calculations. Then here, this profile function omega, which it has this property. So here, so they're looking at the plasma of this n equal to 2 star. And here, plasma is cool in this region. So these massive fields are not that excited in that region. So there are several things to check using this lattice construction.
And you said this, but this supergravity solution is only known numerically? Or is there an analytical?
That I don't know. They are solving this numerically, okay? So that means it is not known analytically. Yeah. Yes. So these are the people, Larry Yaffe, then Buchel, so they know about this stuff. Yeah. N equal to 2 star finite temperature. Okay, so let me conclude. So I presented a lattice construction of n equal to 2 star superangles. So we could simulate thermodynamics on the lattice, finite temperature. We could validate gauge gravity duality in a non-conformal theory. This is a big achievement, okay? If we could do this, validating this in a non-conformal setting. So we can study finite temperature properties, first law of thermodynamics in ADS-CFT setting, so we can study that. We can look at thermal phases of the theory. Are there various phase structures appearing in this theory? We can explore that. Then on the lattice side, there are several things to do. So we need to enumerate the symmetries of the lattice theory. What are the discrete symmetries? Can we recover all the supersymmetries in the continuum limit? Questions like that. Study renormalization and fine-tuning of this theory. Again, is there a sign problem in this theory? So one has to see that. One can check that through numerical simulations. Then there is a dynamical or thermodynamic instability, whether that they exist in the system. Could study that as well. So there are more things to do, okay? That's all, thank you. What is that? This is 3 plus 1, yeah, 4 dimensions, yeah. People are already doing n equal to 4 superangles in 4 dimensions. So you need to use bigger computers. So you need to use some clusters to get some sensible results. Yeah. Also parallel programming. You need to use some parallel coding.
So this will be harder to simulate than n equals 4?
I don't think so. It will be same, yeah. Because it's also 4-dimensional theory with less supersymmetries. Yeah.
There are, I mean,
Yes, so one has to look at this dimensionless ratio of M over T, okay, and take that as a parameter and simulate for various M over T's. Yeah. N equal to 2. One could study N equal to 2 as well using this formalism. Cyberwitton, yes, yes, yeah. One could study that as well.
So he wants to do thermodynamics.
Yeah, I want to do this at finite temperature.
From the other side. So from gravity they have a prediction for the
Yeah, yes. We need to check, okay? We need to compare and validate. That is our goal.
So if you want to check it, yes, yes, yes.
Yeah, yes. Yeah.
If you want to check any,
I guess I don't know what the predictions are for gravity or, well, I guess it's not
yeah, basically, what can cyberwitton do? They can compute the very low energy vector. That's it. You ask them what's the finite temperature partition constant of electricity.
Right.
Where was the supergravity prediction used in the lattice?
It is once you write down the lattice action, okay, you need a particular form of the lattice action. That's where it comes in.
Right.
Yeah.
So it was only in deciding the lattice.
Exactly, yeah. Yeah. To tell you what the form of the lattice action you should put in on the lattice. Yeah.
So the point is that then you can preserve supersymmetry without a finite. Right? The point of this Q is that there's a lattice version of the supersymmetry
that is correct, yeah. It is supersymmetry exact on the lattice, okay? Yeah. Yes.
I mean, the problem with many of these supersymmetric simulations is that you have an operator that sort of violates supersymmetry but is relevant.
Mhm.
Completely destroys the thing.
Mhm.
Then
Yeah,
you
yeah.
can't
Yes.
get rid of it. Yeah.
So the one way is called accidental supersymmetry, okay? So if you put n equal to 1 superangles on the lattice, it is not supersymmetric. There is a Gaugino mass term which is generated on the lattice, so it breaks supersymmetry. Then you tune the mass term as you approach the continuum limit, and you recover n equal to 1 superangles. So this is called accidental, okay? So you recover the theory by tuning the coefficient. Yeah. Yes. Yeah.
Okay, I have a slightly related question.
Yeah.
There's this property of n equals 4 superangles
Yeah.
that at strong enough coupling,
Yeah.
every operator that preserves SO6,
Uh-huh.
every operator that preserves SO6 symmetry
Mm.
is irregular.
Mhm.
And therefore, if you just preserve the SO6 isometry,
Mm.
you will automatically preserve
On the lattice.
on anything.
Right,
No,
right.
No, it will not be on the lattice.
Yeah.
It will automatically flow to the right.
Okay, okay. If you preserve SO6, okay.
You-
Yeah,
because
yeah.
There is no deformation
Hmm.
that violates, that breaks SO6.
Yeah.
That preserves SO6,
Hmm.
but breaks supersymmetry and is red.
Mm-hmm. Mm-hmm.
So that makes it sound like that should make it easy to simulate.
See, the thing is, on the lattice we don't have SO6, okay? On the lattice,
Oh, you don't
what we have is SO4, okay? The SO4 subgroup of SO6, so that's what we have.
Why can't
we don't
you
have
get
the
full global symmetry?
That is what twist does.
So he's saying without it, we just take leaves of n equals to
Just-
superangles.
Okay, naively put it on the lattice.
And then
Then you impose SO6.
Yeah, I'm saying that the extra operators that you're effectively adding
Yeah,
that break the supersymmetry,
right,
as long as you preserve the SO6 exactly, will all be irrelevant.
right, right.
And so you won't have to do a tuning; it will automatically flow to the.
Mm-hmm. That may be possible. Yeah, I had to think about it.
For instance, the kind of operator you might worry about
Yeah.
is the Konishio.
Konishi, yes, yeah.
And that at weak coupling you have to worry about it because it's dimension 2. Preserves SO6, it's dimension 2.
Mm.
But we know that at strong coupling,
Mm.
it has dimension order lambda to the 1/4.
Mm.
So you've got a large enough lambda, you're fine.
Mm-hmm. Yes. Yeah.
You're saying all those operators become streets.
Yeah, I think you can prove this. So there's a paper by Strassler proving that at strong enough coupling, it's just a kind look at supergravity.
Mm-hmm.
So there is no operator that preserves SO6 and that is relevant. That is relevant.
Mm-hmm.
You just preserve SO6 in the time. You automatically preserve.
Yeah, yeah. Yeah, this is something to think about.
I think ICTS has left by now. They were there till the